Hello, welcome to another video. Hopefully going to be finishing off the read instruction of my virtual machine for the Z machine. So we've got most of the way through the read instruction. It's quite a complex instruction, I guess. There's a few different things doing it. It refers to like the three different parts of the um thing I want to do this, I think. Hide the fact that I've got a thing there, even though it was pretty clear that it existed. Oh, weird, it goes like big clock mode if you have like just a tiny bit more space, just on the threshold. Um, so yeah, last time we got to a point where it's crashing on the Lexa 111, which is that line there. So, yeah, last time we basically got the Z string encoding into a data word. So now we need to basically do a dictionary search over the past table. So the past table has what is it, info dump. If we do something like well, actually, if we just do something like that, we can do show the dictionary, and maybe we can even go like this. So the dictionary does have quite a few things in it. Uh, and it's got a dot and a full stop, so our sample input should kind of pick that up. And yeah, it's basically got a bunch of stuff. It's got 697. We start at 1. So what I'll do is just check in the dictionary part. It'll say how many uh, length. So entry length. Yeah, so we should probably start doing this part, but the count of it should always be uh, the right number, pretty much. So I think for this, I will perhaps make a new dictionary .odin. I'll make a new Odin file, and you need what package and where in Odin's, and I think that's all you need to have a thing. But before we do that, I will do something like um, what do I want to do? I probably just want to find the index. So index is going to be dictionary, and we can search for, and we're going to pass it machine, and we're just going to pass it data. And that should do the trick, I think. And in this part, we can probably just, well, that's just what it's going to do. And in dictionary, we probably need to make that function or procedure. So what we call it? We called it dictionary search, and it's going to be a procedure, and it's going to take machine, which is of type machine, and the headset back end thing. And we're also going to take what is that other type? Not that type, this type. So it's just a U16 slice. So our data is just going to be a U16, but it's going to be a slice. And it's going to return, what are we going to return? I mean, we could probably just return a number. So, dictionary entries. So there's just as many as that, I guess. So I guess index of 0 we could probably say means nothing. Just looking at how the not that one. Go there and go up. Yeah. If we look at what info dump spat out, we can see that it started at 1. So we could probably just say an index of 0 means nothing. And that had more than 200. It had 600 something, so it had more than what can fit in a byte, 256. Not including, well, including the 0. So, what do we need to do in the dictionary? I think we do actually need some stuff from one of these functions. Yeah, this guy here. So what does the dictionary have? That very first entry is in. So we need to get that in because we want to skip over in bytes to get the length. And we probably want to assert that the length is the size of the bytes that have been passed in divided by 2, I guess. Because, yeah, we just kind of made it a U16s, and so there will be, because the words are all, well, like the Z strings always come in pairs, so there's always going to be an even number. So this is going to say it's 9 Z characters and divide by 3. That's 3 Z words. So I guess this, yeah, we'll just see what things look like, but we'll grab that and we'll go back to where we were and get that. And so what's the other field we need? Length and count. Sorry, I just had lunch. Well, it was a quick lunch, so I've got some burps. Hopefully they don't come through. So, I think I potentially want that there just to kind of see that a bit clearer at the same time. So this is going to be machine read bytes. It is a byte. And what are we going to read? We're going to read at dictionary, but we're going to add n, and we're also going to add 1. So that's going to be, the n is this list, which is n bytes, but then we're also going to add 1 for this byte that we read, which had n in it. So that should get that address, and then we probably want to do count, except count is what, a word, and this is going to be count plus 2, because it is straight after. And I think what I'll do is, well, we can probably do an implemented, see if that kind of will let me do that. So I think I want printf line, and I'll go length equal what is it, percent. We can just do percent %d. In fact, we probably don't need to do this. We can do length length and then count count, and it will just space separate it for us. And they'll probably complain because we have not imported what is that we need to for FNT with the single colon, I think. Yeah, single colon, boom. It looked slightly odd with the double colon. Right, so it doesn't like here. We need to maybe cast this to be a U32. And that will probably just work perfect, not yet implemented. So if we, I don't know what I did there, hopefully not much. Right, so here we can see the length is 7 and the count is 697. And if we do this and just grab the head, we can see length is 7. We've lost where it is. So word size is 7, length is 7, and count is 697. So boom, we have successfully read in 2 bytes. Well, a byte and a word. But from here, what we want to do is I probably want to do something like this and set entries to be dictionary plus n plus 3 plus 4 actually. So that will be basically the address after this header, because I believe it just says doesn't actually say yeah, the word entries follow immediately after the header and must be given numerical order of the encoded text. So because it well, actually we wanted to do an assert on that count, I guess, which is 7. Does that seem right? That does not seem right. What does it say about this? Entry length is the length of each word's entry in the dictionary table. It must be at least 4 in versions 1 to 3 and at least 6 in later versions. And that is because it has 6 Z characters, so but this has length of 7, so does that mean it has 7 bytes? Yeah, so I guess it's 7 bytes, and then you have some random data. So I guess what we can do is assert that count is greater than len of data, because we can ignore this data, so I'm happy with that. Length of data divided by, actually no, multiplied by 2, because we've just got a 2-byte array. Where do we have it? data down here. So we will either have a 2 or 3 byte, 3 word array, and we need to make sure that it is more than the length. So the length is currently 7, so we need to make sure that 7 is more than 4, because 4 is the actual number of bytes we have. I made it maybe a bit complicated by having words, but that's all right. Gosh, will you not let me go back? Cool. There we go. So now that we've got the address for the entries, yeah, it did go to the unimplemented. Well, actually, we can confirm this. It does not like that. I don't remember why that went away. Right, I think we can probably safely just convert that to an int. I think I want to just disable that line. It's like somewhat helpful, but I want to go to the first. Well, it automatically jumps to the first line error tagged with the location, which is here. So this is where I want to do some searching. So I guess what I could do is maybe just for now, to make sure that I have the right understanding for the entries, just loop through. And yeah, so there must be just random data. I don't know what the data does, but it is what it is. Um, I think I want to change data to be maybe like needle. Um, Actually, let's not do needle. Let's just do search. Because there's also the data in the entry, and I don't really want to overload it. So yeah, let's just temporarily kind of go through the what are we? Do that. Go through all the entries and maybe print them out. So if we do something like this, and I plus equal 1 and get something like that. So in here we can probably get the entry, which is going to be, well, it's going to be the entry header, and that's not what I wanted. I want that, and this is going to be entries plus, I guess, length times I. And that seems right because the first one is going to be, yeah, the first one's going to be that. Um, so we do have a Z string dump, so I guess we could do something like format.print that an entry, and do might do I plus 1 just to make it consistent with the info dump. In fact, that's what I'm going to be returning. Yeah, I don't know, off by one errors, one index, zero index. It's confusing and computing. So we can probably from here just do the string dump and just print out the machine. So I believe this needs a machine at just the address. It might just need that. Oh, and it also needs a thing like that. But I wonder. No, I want that, but I then want to do that. Um, that's what I wanted to do. No, length is just defaulting to 0. So we don't actually need that. So we can do that. And I think we can also do something like this. And what data will we pass to it? Though here I think I want to do print f and maybe ln because that will be printing out a bunch of stuff. So here I want to, it's going to be in bytes. So I think I want to make sure it's always 2 nibbles, 1 byte. And do something like that. And I kind of like this because what I'm going to pass in is just a slice of the uh, memory from the entry's address, but not from the entry address, actually. We want the entry address plus. Uh, I'll just hard code it here, but maybe we can do an if header dollar greater than equal to 3, do unimplemented just in case, because we are hard coding the address there. So then we can have this being length minus 4. So this cool syntax is like you're taking a slice from a certain point to the end of the array, and it's not copying anything or anything. It's just taking a point reference to the memory and saying this is the length of the reference you're looking at, and then you then take another slice from the start to a certain length, and so that's kind of taking a chunk, and you don't have to do like weird arithmetic to say. Otherwise, I'd have to do something like entry address plus 4. Well, yeah, what would it be? Entry address plus 4. Well, length minus. I don't know. It's just easier doing it this way. My brain can't cope now that I've seen it. But yeah, that should do that. And I wonder what this will print now. It will complain. I think I'll maybe go back to, no, I just wanted this over here. Right, so I missed a bracket. Yeah, just a bracket. Right, doesn't like this because cool. I think we can safely just cast that to an in. It's kind of interesting because unsigned integers should all like kind of theoretically always be castable to an in. I guess maybe not because like well, from what I understand from Odin is the integer. Actually, no, I might be wrong there. But anyway, a U16 should always fit into the integer space here. But I think if I look up this and actually, no, it'll be everywhere. So basic types. Int is just an int. Yeah, so int types are the natural register size. So it's theoretically could be U8. You don't know. So yeah, I don't know. I'll just do it. Right here, it doesn't like it. I think actually what I want to do is uh, maybe just make these U32, and that should probably just make that, because entry address needs to be that, and this can probably just be U32 of 0. In fact, I wonder if it'll just magically know. No, it doesn't. So U32 of 0. And so now, ooh, it doesn't do it. No, if it's greater than 3. So here we print out a bunch of stuff. I might do some print effing and do not that, just D, and do that with a space, and here I will probably also do maybe like a new line and like a tab. I don't know, make it fancy. Um, so here we can actually no, I think I don't want the new line. Um, maybe just a few out from the word. It does make it look a bit funny. But oh well, it is what it is. So I guess if I go down here, we can maybe do something like this. This can probably come off a bit, come over a bit, I mean. So that's kind of what it needs. Maybe a touch more. So it does have like kind of data doing things, but as it said, like we don't need to care about the data. It says the interpreter ignores the data. Presumably, the game pass will deal with that. So what I'm really seeing is that these words are looking about right for that. So we are skipping over the right things, and we've got a way to do it. So in by design, they should be somewhat in alphabetical order. If it's got special cases, yeah. So the last one's Z, but the first few are like if it's got special cases, and that is because it needs to get to A2, and to get to A2, you need to push what is it, 4 and 5. So you need to push 4 or 5. Um, so and that is below 6. And then the order of this is who knows, but I mean that seems to be the order that was in the thing. So I guess what a very naive approach would be is to compare the search term. So we're just kind of searching through. Um, I think I want to maybe start doing this encoded length, and this is just going to be what are we? I guess a U32, and if headed dot version, because they are pretty much the same. That one, thanks. If it's less than equal to 3, we can make encoded length equal to 4, and we can get rid of a thing. Otherwise, do something like that. Otherwise, we or what length was it for? 6 characters, 4 bytes, 6 bytes, 9 things. So this will be just no, that, thanks, 2 more. And here we can probably go back here and replace the 4 with encoded only. Makes the line a bit longer, but it is what it is. Was there a Z string dump that got me just the Z string? Yeah, so Z string read, we can just do that. So we could probably do something like this. That, and maybe go like back, no, find that and make it a line, and here we can probably do something like this, and oh no, not that one. Lost my train of thought with that. And read is what I want, and here I can just go to here. Did that not do the trick? Read, no, we just need to pass no there. And then we can also just do like that. Not that one, that one. And that kind of makes it a bit nicer, and it should still work and print all things. So yeah, very nice. Oh, sorry, that I linked to the thing and announced my presence. So there's 700 things, and the read is kind of used somewhat, and I think it did say that this was also used for the tokenize, but also just the read. I guess the read is used every time that you use give some input, which is typically a slow thing, but the user also wants a quick response from their actions so they can spend more time reading, I guess, because these are text adventures and you got to do a lot of reading. In later versions, there's some visuals as well, but in these earlier ones, it's mainly just reading. Well, reading and writing, but the reading is when you want to start thinking about what you're doing. So, one way to do it, which will be a bit slower, is basically loop through each time and find whether the search term is in there. And because it's ordered uh, like because it's kind of ordered. What am I trying to say? It's ordered like in order, numerically. Um, you can bail out once you reach the condition, which might make it a bit shorter, bit quicker. But there is the worst case that you don't actually find anything, and you will have to kind of iterate over the entire 700 entries. Um, there's also a quicker version, which it does kind of suggest. Maybe it doesn't suggest it there. Maybe it suggests it here. Input done stuff. Looks it up in the dictionary. Gosh. Searched in the dictionary. I'm sure it mentions somewhere. Yeah, so you searches in the remarks. So you can do a binary chop algorithm, which is also known by other names. So if we do binary chop, they'll be after you. Um, chop. I don't. I said crop for some reason, and it's a different thing. Yeah, so you may know it as the binary search. So it kind of splits up. That isn't really a great visual. Well, it's somewhat good. Um, it splits it up into two each time. So for this example, you're never searching this half of the array. So it'll look at the middle center element, and it will then test against the number you have to see whether it's higher or lower or equal. If it's equal, it can bail out. And then it will go and then search this half of the array using the same function. So it'll get the middlemost of that array, then look, and then it'll be here. Then it'll get the middlemost of that array, then it'll look, and then it'll be here. This array only has one element in, so it must be that. Um, and you can also get to a point where you don't find anything. So, say if this was searching for nine, it would say that would be 9 is greater than 6, but this would be 9 is greater than 8. So then it would search this array, and then 10 and 13, it would find like 10 or 13, depending on which. And we'll say it found 10, it would say 9 is less than 10, and then it would be searching on a zero length array, which will signify that it doesn't exist. So I think I want to do that binary chop algorithm because it is quicker and it's good practice to kind of try out new things. When I say new things, I've done binary chops before, but it's good to try out like those sorts of things in a new language because this language is new to me. So yeah, that kind of came out wrong, but yeah, we can probably do this. And how did we do this? We did. Is it that one? Oh, there. Um, was it just private equal file? No, I don't think it was. Uh, we want well, yeah, buff Z string has a bunch. It was close. So I want that sort of thing, and then I can kind of uh, kind of overload it. I'll call it a chop, like it suggests. And yeah, I guess because yeah, um, to speed things up, I'm thinking to speed things up, you could kind of just pass the whole slice of memory to it rather than call the machine read byte. Well, it'll be a machine read word, compare it to the first thing, which is potentially better. Otherwise, you can just get a whole slice of the memory and then kind of search over that with entry size so you can work out the appropriate point to search in. So, potentially do that, but it kind of does expose the like the how the machine works. But I think I kind of like it. Um, and what's this gonna return? I think this should just return the. Ah, come on. It should still just return a U16. Because that's what I decided, I guess. Um, but here we can, so we need the memory, we need the search, but I think we also need entry length. Um, do something like that, and this is just going to be U32 because that's how it is. Yeah, and so I think here, well, I can get rid of that. Uh, I mean, what I could do is have that as just like kind of helper function. Dictionary dump entry, and it can just like pass in the machine. We'll just do that. And also the address. And that's going to be a U32 because that's just what our addresses are. Um, do something like that, not that phrase. And then we can probably just do dictionary, dump entry, machine, and entry header. Maybe with that length as well, encoded length, because it does use it. And this can just kind of do that. And so what do we need to do? Get there and do encoded length. And that was also just going to be a U32, I think, from memory. And we can probably entries. Well, do something like that. I think you can do stuff like no. Um, there are like some different for loops and stuff, but I think this is kind of a bit nicer. And yeah, it just does what it does. And that way I can kind of reuse it when I'm doing the search and I'm saying I'm looking at this particular entry, and hopefully that should say what it is. I guess actually, this maybe I do kind of want to do this, but that's like quite expensive. Maybe I don't want to do any of that. Maybe I actually do want to do all of that. But I just want to do that. And I can just do format dot print entry print if starting to get tired. Entry boom boom, give a space and pass it the I. Though I wonder whether to pass in the I. The problem with doing that is you would have to kind of read a few things extra. This we probably don't need. Well, actually, do we have a Z string read that will just work on? Uh, no, we don't really have one that just works on a slice. That is one thing that we don't have. So I think this binary chop won't really work as I kind of intended. So I think I do need to have the machine. It's going to have a type of machine, and we'll still have the same entry length. Wow, this. Nah, that's fine. That's fine. And I think I want to do a worldwide replace with encoded length with. Actually, no, I don't want that. What am I thinking? So yeah, with binary search, I guess I was thinking of just having that slice and doing it like that. But if we can't do it like that, we need to kind of have a base address and account, or like high and low. So the low is going to be that, and a high is going to be that. And they're just going to be addresses, and it's getting a tad long for this line. The entry length, we kind of don't know. That is something we don't know. How would this be getting called to start with? It will be something like here. Yeah, so I guess the encoded length doesn't really need to get passed in. That's what I was thinking. Detail that, yeah, and then down here encoded something like that. And then how would we call the search? No, go back here. But just dictionary search chop. Dictionary search chop. So this is going to take in the machine. I kind of want it like there. So it's going to have the machine, it's going to have the entry length. We're going to pass in the search again, and the low is going to be the low address, so that's going to be entries, and the high is going to be just past the last address, so that's going to be entries plus length. I'll change that Z. To that, and length times count, and that kind of makes sense. So this will just return something. So I guess here we can probably just return whatever that is returning. And I guess I'm happy with what that's got going through. So how do we do the binary search? So we want to work out the midway. So the midway is going to be it's going to be the difference between high and low divided by 2, but because we're offsetting it by low, so this is going to be our mid. That one, and theoretically, I think so I might just print out what that is. Format.print midway equals and this is going to be mid, and I'll also do was it dictionary dump entry. So this is going to be machine, and just pass in that mid. And I guess it would be nice if the dump did kind of say which entry it was, which does kind of mean that we need to get some of the stuff. I'll bring it all up just in case. So we don't need that cert. So the entry number will be what? Just the entry adder. So the entry adder would have been entries plus length times some I. So that's what it would have been. And if we rearrange that for I, to find which entry it is, that would be what entry editor minus entries, all divided by length, if I'm not mistaken. Um, so we probably could add in this entry percent D is that, and we probably could pass in this as come on, our kind of first thing, and then that dump entry should hopefully show us a thing. And this will probably complain because we're not returning anything. So I guess we can return 0, signifying that we did not find anything. Right, it doesn't know about entry editor. We can probably just call that entry editor. We can just call that address. That wasn't what I wanted. This one was right. It's doing a thing. Right. So it found some midways. So it's getting the same midway each time, and that is 3, 4, 8, and if we so there was 697, 697, and if we divide that by 2, we get 348. So that's a good thing that we're finding that. And I guess if we look up what um, 348 actually looks like, it is leaves, and that is not what it is printing. So I guess that um, that is not quite right. And midway, it's like percent. This is gonna just be maybe 04x. Do something like that. Yeah, that's a bit better. Though, is it? No, that's like not quite better. Do do. Right, 348. But the 448F, that's what it was. So I guess I potentially do want that kind of for loop again. So what was it? It was for I equal, and I think it was U32 of 0. That's not that. And I is less than count, and I will be plus equal to 1, and do that. Do something like this, and what are we going to machine dump? We're going to dump the entry, and the entry is going to be entries plus length times I, something like that. So we will get back to where we're getting, and I think that, yeah, 696. We want to go here and the dump entry. Gosh, it's hard to. That's right. I like made that quite large. Pardon me. Um, all right, where was I in the code? Right, this will be we'll ask one because we're doing offset by one. It's just what we're doing, which I guess kind of makes me think. Wow, I don't know. I don't really want to. I can get length. Yeah. Mm, yeah, I don't know. I don't really want to read lots of bytes because I'm trying to make it efficient, but it doesn't really need to be that efficient. Let's be honest. Um, but what I'm trying to kind of think is we're returning this, and it's going to be the index of whichever entry we found. But in this function, we don't actually have the index, we have the address. Well, we have the low and high, which is not indices. So I guess uh, do this and that. And then down here, the we probably want to have the base. Um, have that, and we can just pass that in, I guess, and then have the low high. So that was like this one, and the low high, sorry, you can't see that. The low high can then just be 0 and length, which I think looks a bit more readable down here because you can see that they're kind of indices. Um, yeah, and I guess this is going to return 0 if it can't find it, but if it does find it, it will have to add on 1. If found, add 1. Because, yeah, this dictionary dump entry, I guess this is going to be the entry number. And I guess it'll just be a U16. And this will be that, and this will actually be entries. Well, maybe I want to do address is equal to entries plus length times entry. Something like that. So it should still do the print. It doesn't like something. That one thing. Right, doesn't like length times entry because they're different lengths. And where are you looking there? You're looking there. So I guess we can just do something like that. Um, And here we can probably just do something like that to make it a nice one-liner for dumping out the things. Do I just want to return a U32? Like, is it possible in here, the 2 byte word is going to be the count. So yeah, I guess it's always just going to be a U16. It can only be a U16. Wow, like theoretically it could be a U16 plus 1, but yeah. And I guess where are we even calling this from? We want Lexa, and this is going to just be getting an index, and we're going to be writing that. So, yeah, I wonder if we just want to do that and call each entry U32, and it will that one, thanks. It will kind of save a bit of hassle with things. So this will be U32, high will be U32. And so midway will always just be uh, it will always just be an index of it. But yeah, we'll see what this does. Can't do that because we're still returning that. Cool. This one changed to that. Right, so entry 4 is not correct. Kind of means that we're passing in 3. Yeah, we don't want length here. We want count. Um, length and count. Yeah, so now we're getting 349, which I guess if we divide by 2, 697, we get 348. Probably, well, we can do something like scale with 2 and 697 divided by 2 is 339. So it's actually closer to 348, but it went 349. But we're adding 1 to the entry. So I guess if we go back here and search for 349, we do get ledge. So it is looking at the right chunk of memory, which is good. Might just comment that out for now, but I can leave it in there to see what it is. So at this point here, we have our midway, and we want to test whether the search term is lower or higher than the entry that we're currently looking at. And yeah, so I guess to figure that out, we need to, because we have search is basically a slice of U16, so we need to read word by word and then compare the index of that part of search, and if it's equal, we go to the next one, and if that's equal, then we'll probably uh, the midway point we're on because it's all equal. But if anything is not equal, we will probably uh, not return. We'll like recurse deeper. I'm not in the right mode. There we are. Mid plus one. So that's going to be our base case, which is like if all falls through, then that's going to be that. But we probably want, we need that, need a loop. We can have I is less than length of search, which is the word array that word slice we're looking at. And we can add in two. And when we add in two, we actually want to start at 0 and only add in 1. Off by 1 errors. I'm actually unsure why I put that in. I think I just put in the 1 because I put in the 1 down there, and you get confused. But you need to know which one is which. So the actual table and the entries is 0 base, but what we're returning is going to be 1 based. So I guess we also have the case if mid equal, well, no, you actually usually do if low is equal to high, we can return 0. And that's really the very first thing that we can do. And here we are doing the search. So we want to do machine read word, and the word we're going to be doing is machine, and we do actually we pass on entries, perfect. So we want to do entries, and I think this length should just be length to keep it consistent. So this is going to be come on back here. I don't know why you had so many tabs. Entries, it will be entries plus length times, and this is going to be the midway. But it is also going to be mid. At the end there, it's going to be plus I times 2, I guess. Because yeah, each word will be a word. So that's the word that we're going to be reading. And I guess if we'll call it word. Rude up, man. And so if search of I is less than word, we'll just return dictionary search chop, and we're going to pass in machine. I think I might actually not do the inline just because go back here, thanks. Just because it will did that add like, no, it just kind of looked like the wrong level of indentation. So we're going to pass in the same sort of stuff, machine length, machine entries and length, and the search are all going to be the same, but the low is now going to be, so we found our search term is before the word, so we want our low to be the same as what it currently is, but we want our high to be what the mid is. And then was there an else if? No, else if search I is greater than word, we're going to do the same thing, um, except here we're going to have mid as the low and high as the high, because this is the search is on that side of it, so we're going to search in the upper half of the binary search. And this is pretty much it. And so this is, if it doesn't find it, we're going to return 0. Otherwise, it will figure out the midway. Can probably do that. I don't know. I think I kind of want to go to Lexa and do no, go back to Lexa and down here. I want to kind of just do format dot print and word and pass in the word that we're actually trying to do. Doesn't like that. Right, U32 and int, so I guess it's just the I, isn't it? Right, so maybe just make that old boy U32. Cool, so it had an endless loop. So we can see here it's kind of jumping over the show, but at one point it just kind of keeps on going the same way over and over, which is not good. It kind of means that it's not doing that. What are we doing? The space check. So what I might do is low equal to d. High equal to d, and midway equal to d as well, and we can just have low, high, and mid, and we can probably make that a line. Cool, you segfault, but we probably need to have print F there. Segfault. So what's happening here? Low, high, midway, low, high, midway. And when it's just getting this. So the word we're looking for is high with a bunch of things. So I can kind of imagine it kind of looking at these words, but it does kind of just go to 8 after a while. So when it's 287, so yeah, so low isn't the same as high, but midway is the same as low. Which kind of means that if it's not midway, it should be searching one up. So I think I want to just chuck in heaps of stuff. Less. Just to make sure I understand kind of what is happening. Because at the moment it's doing a endless loop, which is not what we want. So yeah, It is more than high. That's kind of what I've forgotten. So the high point is one past where we're going, which means that when we're searching above where we're going, we actually want to search from mid plus one. And I think that should do it. Yeah, so that kind of gets to after the index. Um, so I guess here we can probably write out what the index was that we found. And maybe here, maybe not do that. And it should be reasonably clear kind of what's happening. So we've got high, we kind of search through, and it only searches what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 before it knows that it's not there. So it doesn't search that whole 600. So that's the whole kind of point of the binary chop. And it finds that index is 0. This high with lots of things is not in there. A comma, it should be quite close to the start. 1, 2, 3, 4, 5, 6, 7, 8. It finds it for 3. So it did actually search 8 more than 3, but on the average case, it should be a lot quicker. So, in complexity terms, you would call something like just a loop over it all is order n, whereas this type of algorithm is order log n. And you can tell it's a log n because it's splitting up the array. Um, so it's never actually kind of scanning over the whole array. It's splitting into chunks. So that makes it log n, which is quicker than n. If you do something n times, it's significantly longer than just log times. In fact, a factor of e. So it would be like e to the power, like it's exponentially longer. I think is what I'm trying to say. So here, this doesn't find this is it does find is uh it finds test. It does not find test. I'm pretty confident that this is doing the right thing. Feel, yeah, it has that. Free has that. 2 has that. Say has that. Quote mark has that. High did have that. Um, and the end quote mark it had that. Dot it had that. And then, yeah, here we're at the binary search. So that did actually take a bit longer than what I thought. So what, hour and a half in. Do I have the mind power to kind of do this? I think I probably do. So looks it up in the words. Then we're writing a parse table. So the number of words is written into byte 1. And I guess there's no byte 0. Oh, well, no, byte 0 of the parse buffer should be the maximum number of words that can be parsed. So I don't think I actually ever read that. So in our Lexa, yeah, we never actually read that. So I guess the Lexa split should, well, maybe not the Alexa split. like we split the words, but I guess we could probably pass it because it already reads it. The split is really just to get that. So I'm wondering if instead we um, do something like this, and this is going to be a pointer to a slice of strings, and don't return anything. So here we can not have that rect. Where do we actually have a rect? We had this append, so I guess we have an offset and index. Index is that. Offset is a different thing. I think we need to have another thing, results IDX, and this can I might do that, and this can initially equal to 0, and here we can have results I no results this, and results IDX, and this whole thing is going to equal to input index that, and these ones thanks, and do something like that. We don't need that. And here we probably need to have result IDX plus equal to 1. And I guess if if result IDX is there's like kind of a few if result IDX is greater than the length of results do return, except greater than equal, I would say. And I think I want to replace this thing with if len word greater than 0. Do this actually, and results. It's kind of annoying. It's like from the line below, but I want to make this all one insert. Though it's just that results IDX plus equal 1, and if results IDX greater than equal to the length of the results, boom, do return something like that. And then here we can just do the same. No. I also wonder if I meant to have that sort of thing. but yeah, I guess this is kind of what I want for there as well, and this. Um, that, and then that. Don't need to do a check. Don't need a return. Don't need to bother with that. Um, but I guess this probably should happen there because it's pointless actually doing it. So I wonder if this kind of broke things. Do that, so we'll complain about that other one, I guess. So that's going to be the same for there, and probably there, but we can do that a bit more manually. Cool. Right, so here we kind of want to make the words, so we just want to be the ones that make and this is going to be a string slice, and the length of words is stored in where did I see it? Byte 0 of the pass buffer, maximum number of words that should be passed. Pass length maybe, and that pass length can be machine reads bytes from machine, and read from just pass. Thanks. And here we can have a pointer to words, instead of doing that. And we can defer a delete to that. And they'll just kind of limit it just in case it did do something. Right, so it doesn't go past me. That is because we need to declare it there. Cool, so here it is not doing the right thing. Yeah, that the word is just blank. Blank is blank can be. What is pass length? Print line. Pass length. And implemented just to make it stop there before it goes to anything else. What was it? 120. So it should be getting a bunch of words. Um, we're passing a pointer to it, so it should be kind of writing to it. We're still in the scope. What does words have in it? Come on. brain is not doing the right thing. So it does have like a bunch of things in, but it has a bunch of blank lines at the end. So I guess well, that's like the maximum number of words. Maybe I don't want to do any of the changes that I have done here, and I'll just split all the words. Yeah, I'll split all the words. But I guess for the past table, yeah, maybe I want to truncate it after, or no, this is what I want to do, I think. Limits can be machine, read byte machine, and has, and we can just pass in the limit. And here we can, not here, this one here. If length of rect is over the limit, to return rect. And they'll just continue. We do want to do a special case here because we we do two, potentially two things. And same thing here, don't do that if we do that. And that should just magically work, except we do need to pass in the limit, which will be a U8, and which will probably make things complain. Here, we'll just let it complain and tell me where I need to do things. So we can just convert that to an int. Just go to the next one actually. Do that, and then do that, and do that, and do that, and that should be all right. Yeah, cool. So that's doing things, and the word is getting some words, and it is getting indexes of the words in the dictionary. Cool. So do we need to overwrite that word, I wonder? Number of words is written to byte one. So we can probably just do machine write byte to machine, and we're going to write to paths, and we're going to write the length of words, but casted to a U8, which that's just what it will be. But it will actually be pars +1, won't it? Because 1 byte. And then so 1 4-byte block is written for each word. So I guess because it is doing something there, I might just have a table, not a table, kind of address. What are these called? Just a block. pass entry. So this can be pass plus 2. Um, and maybe we'll chuck that down here. So we're getting the entry and what the block. So it's the byte address of the word in the dictionary if it is 0 or 0 if it isn't, followed by the byte giving the number of letters in the word, finally a byte giving the position of the text buffer. That's kind of annoying that we actually want to return the address. Which, yeah, I potentially should have read that. So the pass entry, so byte header is going to be a word, and number of letters in the word, and position in the text buffer of the first letter in the word. Oh gosh, I'm not sure I have that information. So it'll be len word u8, u16, and this is going to be right, byte first position in text buffer, text lock, IDX, I guess, and that's going to be a U8. So makes me wonder. This split, it knows the text offset. It knows it indeed. It's looking at it index. Actually, no. Yeah, so that's the index of the thing. So I wonder if instead of having a string, we have maybe a like parse object, which might be private, I guess. So this will be that one, then private equal to file, do that, and this will be a nice structure. So we'll give it an uppercase. Do we want to call it Alexa? It's kind of like a parse block. Lext lock. I'll call it that. And this is going to be a structure. And what is it going to have? It's going to have dict adder, which is a U16. It is going to have a length, which is a U8, and it is also going to have a index, which is U8. And did they need to be commas or something else? I don't know. I'll let it. Commas are fine. So, instead of string here, I think this should return a lext block, which it can't do because it is not the right thing there. What does it complain about now? Doesn't know about that. So what we could do is something like this, and well, I kind of want to have the actual string. well, no, that's going to be word, and it's going to be a string, something like that. And we will know the index, the length. Actually, I'll keep those the right way around. So the word is just something that we will kind of use. So at this point here, I wonder if we can just do something like word equals word and index equals index offset, which would mean that would need to do that there. And I wonder if this will know what the fuck we're on about. No, it does not. How do we do structures elsewhere? So we have a lot of instructions. It's just the same thing, but what if we do an actual space? Right, so we have a header, we have an operand instruction. Maybe I will go have a look at z string, the z string. So what's the struct? We have a z string. So we just pass it a thing. And so we just give it the name of the thing before those brackets. And so that is going to be a next block. And give that a run. It doesn't know this. That is because we probably just need to make that a UA. Kind of limits you, doesn't it, to link like a length of 256 or less input. Cool. So this is going to be a similar thing to this thing. So maybe I'll yank and find that one. Yeah, that's the one I want. And maybe just do that. And I should have yanked it into something different because it has now been unyanked. Find that, yank that. I knew it. I knew it. Lex block. Word equals word index equals to U8, and this is going to be offset. And do that. And here we also have an append. This is going to be a next block. But here the word is going to be equal to this thing, I guess. And index is going to be equal to index, I guess. And that should be that. And that's just because it's a character. Yeah, so that's because it's a character, and this is a space, so it doesn't care. Um, cool. That should return us a bunch of Lex blocks, which should complain about things. It doesn't like that because we don't have that. Um, right here, we probably want to get word dots. Word. Um, so this is going to be word dots. Oh, yeah. So we want the byte address. Of the thing. So that's still looking like it's doing the right thing. So yeah, this dictionary search, we actually want this gets the index of it. So from the index, we actually just want to return if index equal to 0, do return 0. Otherwise, we want to return entries plus length times index, something like that. Yeah, so I think that's all we kind of need to do. And here we can probably, maybe instead of calling these words, call them blocks. That is the something like that. Right. And that way we can see what it does. Right, it doesn't know about words blocks. It doesn't like that because we can't assign it. Haven't used that feature yet. We don't want index there. We want dict address. So I think could probably do that. And maybe just do a print line of the whole block and see whether it's got something that we can write out of. So we're going to downcast that to U16. That's all right. Maybe let's do a go back to um, undo that and that do a printf and percent 4x, do something like that. And so It should be getting 0 for some of them. So like this one, it should be 0. Yeah, cool. It is 0 sometimes. Dict address 0. Cool. So it is 0 sometimes. The length is not set. We could probably do something like length equals length of word. I think I want this. We'll still call it a block, but the block will not have the dict address and length. It'll just have that index. So then we can kind of do it. That was still blocks, wasn't it? Cool, lots of changes. So just to confirm, we do have some zeros, perfect, and here index is looking like it's kind of going up in order. Bar 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so that will be index 8. Will it? Yeah, it's because there will be 0, 1, 2, 3, 4, 5, 6, 7. The next one will be 8. Perfect. So this looks like it's working. There was a space after the 8, so then that would be 10. Cool. That's looking good. So I guess here we just need to do machine write word. And what's this word going to be? It is going to be to the machine, and it's going to be to pass entry. And this is just going to be the first 2 bytes. Should stop before going to the max, that's fine. So that's going to be the byte address of the word. So this is going to be the word, and it's going to be the address. Then here we're going to write a byte, and this is going to be byte pass entry +2, I guess, and this is the second part is number of letters in the word. So this is going to be length of block.word. And here we're just going to have that, and the last bit will be block.index, I believe it was. And here we probably should do pass entry plus equal to 4, because it's a 4 byte thing. And then version 5 and later we should potentially do like a thing. So I think that is done. Done. Right. Let's run it and see what happens. It doesn't like that. No, this needs to be U16. That's all right. And this can be U8. And I am aware of the consequences. Do this. Right, so now I could probably in dictionary. Could probably not do the dumping. Dump. Do something like that. Cool, that looks good. And here it is not yet implemented, so that is just after we analyze the text. So this is if header dot version is greater than equal to 5, do implemented store. Well, in fact, the store potentially could be kind of easy. Terminating character, so should be either enter or 13. Yeah, I think this is finally read done. Cool. And so now is wanting 2004 at that address. So what I normally do here is look at txt and look at 5932. It's a dict check. And it probably should be after a read. So we had in execution some commented out stuff here. So I think I just want to uncomment this and then run it to see what is happening. So we do the read here. We do a bunch of other stuff, but we do the read. And then we do load byte, jump 0, store, and now we've got dict check, which looks legit. So we just need to look up 2op4 and make sure that that is correct. And 2op4 is dict check. So perfect. That has basically got reading done. And by golly, this will probably be quite a large one. I will comment that back out actually. Go back here and then BC down. So we add a Lex block. That's fine. We do a split and we have a limit. We make sure that we check the limits at appropriate points. And that all looks good. And here we get the limit and we make blocks instead of words. And we write how many we got back. And here we go through, get the encoded string, we look it up in the dictionary, then we write out the block, and then we have implemented it. Cool. And I guess I just won't add that one. But there is a new file, isn't there? So what is, no, we just add it. And this adds like a bunch of stuff. So it adds a dump. We never actually use it anymore. We've got a comment there just showing how it could be used. But that is that. So could potentially just remove it, to be honest. It's not too much hassle to re-include it. And if we, come on, go back and run it, it should still crash at the same point. Perfect. You can do it, bud. Don't add that. So here I should be able to. Is that all from one file? Yeah, that's just what I removed there. Get rid of that. And that's all the stuff that I looked at before. Won't add that one. Finish. Read. And maybe some exclamation marks. Because we did it. It has finally been done. Doesn't print anything back to you, but now we can run some stuff and it will crash at a future opcode. So just need to go on and add more opcodes, and then eventually more text will print, probably saying, I don't know what you meant by whatever my input is. It is hi, this is a test, feel free to say hi. It'll be like, I don't know what this is. But that will still be heaps more progress. So I'm pretty happy with that. Bit of a long video, but I'm happy that we got read done. I'm pretty comfortable that all the three major steps are done. So we had to split the words. We had to write various tables. This had it. So we had to read the input, we had to split the input, we had to split the input on certain terminators. We then had to look up in the dictionary to see if it exists. In later versions, we might have to do stuff with timing, but for now, yeah, just do that. And yeah, version 5 and later, you also have to do some weird stuff with continuing from interrupts, but we'll leave that. Yeah, this looks pretty good. I'm happy with it. Next up is deck check. So for now, I think that's this video done. I got what I achieved, what I wanted to achieve done. It took a bit longer than I thought, but it is what it is. Thank you for watching if you made it this far, and hope you enjoyed it. Let me know, and we'll see you next time. See ya.